Hello students, let us begin Module 5, Vector Spaces. What is a vector space? A vector space is a non-empty set with these two algebraic operations, addition and scalar multiplication. Here, a scalar means a real number. Yes, sometimes we do consider complex vector spaces and complex matrices, but those are rare. And in this course, we're not going to deal with those kind of examples very often. When they are necessary, we'll make appropriate assumption for that particular problem. Otherwise, everything is over R in this course. Now, these two algebraic operations, addition and scalar multiplications, must satisfy these 8 algebraic rules. And they're all here in the same viewing window. Is everything familiar to you? Have you seen these before? Have you worked on these before? The answer should be yes, yes, and yes. As a matter of fact, I assigned this problem, every single one of them as a matter of fact, as a homework set in week 2. Of course, I didn't use the abstract term of vector space there in week 2. Instead, we confine ourselves to this particular case, Rn, the set of all n tuples of real numbers, and then we define appropriate vector addition and scalar multiplication. And then, based upon these, we set up and proved all these algebraic rules. Remember? Well, that was week 2, and it's already week 5, so I guess everybody must have completed and submitted homeworks and must have received graded homework by now, so let's say 1.2a completed by now. And then let's move on to the next example. Prove that the set of all n by n real matrices, capital M of n by n, is a vector space. Let's see, is this a vector space? Have you done this before? Again, the answer is yes. We have done it in week 3, in module 3, when we started matrices. We established matrix addition and scalar multiplication like this, and then we went through all those rules. So we'll say 1.2b is also done, and let's go to the third example. Prove the set of all continuous real functions C0 R comma R is also a vector space. So here, each vector is a function. And what kind of vector addition and scalar multiplication do you have? As a matter of fact, we have been doing the same thing since college algebra days. Adding two functions, add up function values, multiply a constant. Well, multiply that to each function value. Yes, we have been doing this from, as a matter of fact, not just college algebra, from intermediate algebra we have been doing this. And based upon these, can you prove that this is a vector space? By proving these 8 rules. I'll leave the details to the students. It's not too difficult, not too long. At some point you'll have to use the real number arithmetic, but that's about it. Let's take just a little bit of class time for a digression here, because we're going to have to use this as an example for the next topic. Anyway, C0 R comma R is the set of all continuous real functions, but let's consider C1 R comma R, which is differentiable real functions. As a matter of fact, a little bit stronger than that. Continuously differentiable real function, which means the derivative exists, but also all the derivatives are continuous. And then they form vector space, based upon same algebraic operation, of course, addition and scalar multiplication. And that's not all. You can consider C2, C3, C4, and so on, or CR in general, differentiable R times, and the R's derivative is also continuous. And of course, infinitely differentiable. And needless to say, we'll have this kind of inclusion. And this is the biggest set of all continuous function, including something like absolute value kind of thing. And then this one is differentiable, continuously differentiable, and so on and so forth. All these are vector spaces, and all those are based upon same algebraic operations. I guess I spent a bit too much time here. Sorry, I sometimes get carried away when I deal with some examples from analysis because my specialty is analysis and sometimes I just can't help it. Let's come back to algebra. The next topic is subspace. A non-empty set W of a vector space V is called a subspace if W is also a vector space with respect to the same algebraic operation. The key word here is the same algebraic operation. If we have two different algebraic operations, then V and W are unrelated in terms of vector spaces. As sets, one may be subset and then the other may be superset, but if we have two different algebraic operations, they are unrelated. Here are some examples of those subspace chains, and this is Rn, so nth tuple of real numbers. This is Rn minus 1, so n minus 1 tuple. So you can consider in nth tuple the last entry is kept 0, and then this one, last two entries are kept 0, and so on. And then R1, just a set of real numbers, same as scalar. And then I've never seen anybody writing this 0 as R0, but this is a vector space too, believe it or not. You can prove this just set of 0, set given by 0 only, is a vector space by actually going through all these. You can prove all that. Just plug in U, V, W, they're all zeros, and then make sure that space, the 0 space, satisfy everything here. Trivial space, or some people call it 0 space. Another example, okay, the example from analysis, we went through continuous real functions, continuously differentiable real functions, continuously twice differentiable real functions, and so on and so forth. Yes, we have a chain of subspaces like this. Okay, so much for subspaces or their concepts. Now let's go over to some technical detail. Given subset, how do I tell if it is a subspace? Well, this is a conclusion, but let's think a little bit. Given set, how do I prove it is a vector space? Well, we have to get this addition and scalar multiplication, of course, but then again, the key is to prove these 8 rules. That's what we did for these examples, right? But then again, do we have to do that for subspace? The answer is no, and it is a waste of time. Why? Because W is a subspace of V, so the W is a subspace of V. So if I select anything from W, that means they belong to V as well. You see, this is bigger set, this is superset. So what do you mean by that? If you just go over to these algebraic rules, select any vectors from W and put those here, because they are all members of V as well, all these follow immediately. There's nothing to prove. It's always the case, which means there's no reason to go through these VS1 to VS8 because they always hold. That's completely waste of time. What do we have to check? You have to check these, whether this addition and scalar multiplication are well defined in W. In V, of course, they are well defined because V is a vector space. W, on the other hand, we have all those algebraic rules, VS1 through V8, yes, but well-defined addition and scalar multiplication in W, that's not clear, and that's something we have to establish. So close on the addition or well-defined addition, close on the scalar multiplication or well-defined scalar multiplication. Those are the things we'll have to check. So our textbook author calls these two conditions. Addition is well-defined and scalar multiplication is well-defined. If we have these two rules, then W is a subspace. But then again, I did something odd. I added one more condition here. 0 is in W. Why did I do that? Our textbook author said these two are sufficient. Why did I add one more? By the way, clever student would have seen already by now that this one is completely unnecessary, because if we have this second condition, you can always write 0 vector as 0 times some W, and that's in W because of the second condition. So this is always true if we have a subspace, if we have these two. But why did I separate this one and then ask you to go through one more additional step? The reason is very practical. That is, by taking this one arguably unnecessary step, you can make a lot of problem a lot easier. How easy? Let's check it out. Here's an example problem. Prove or disprove the given set is a subset of R2. And here we go. Set A is given as follows: x comma y, where 2x minus 3y is equal to 0. B, x comma y, where 2x minus 3y equals to 1. So how do I tell whether A is a subset, they're all a subset, A is subspace or not, or B is subset or not? My suggestion is, before anything, try this. Plug in 0, 0 first, before anything. That's why I inserted this condition. So let's do that. Plug in 0, 0 right here. X is 0, y equals to 0. What do you get? 0 equals to 0? That's okay. So 0 is in there. So it's possible that this is a vector space. This is a subspace of V. Which means we'll have to go through this one and that one. Okay, all right. So plugging in 0 did not really contribute to anything, but then again, how much time did he spend? Less than 10 seconds. Now let's go to the next example. Considering these two, well, that's going to be hard, but before anything, do this one first. Plug in 0, what do you get? X is 0, y is 0, what do you get? Just plug those in. You get this. 0 is equal to 1, so no. 0 does not belong to B, so B is not a vector space. It's not a subspace. You see, the answer popped out immediately by plugging in 0, 0. And how much time did it take? 10 seconds? Okay, writing everything down may take a little bit more, so okay, maybe 20 seconds. Or if you're a slow writer, 30 seconds. And that was enough for this problem. You didn't have to go through these two. So just by checking this, you got the answer right away. And that's why I separated this one and then just threw away. I threw it in as an additional condition, because this may not be necessary on its own, but it'll make your life a lot easier, especially when you have to disprove something. This third condition, this one, SS3, will sometimes do a yeoman's service. Okay, now that we are done with B, thanks to this third condition, let's work out the first problem. Plug in 0, 0. Yes, 0 is in there. Okay, which means we'll have to do these two. Ready? Okay, it's a subspace and we have to prove it. And then the third one, that was easy. Okay, all right, that was easy. Do this before anything else. Now let's consider the first thing. You have to select two vectors from A and then add them up and see if the sum is in A, which means That's something I'll have to do. x1, y1, x2, y2 from A, and then add them up is the sum also in A. That's what we have to prove. But then again, it's a little bit difficult to work this one out because it's a logical statement. So let's use this condition, which is equivalent to this x comma y belonging A, and change this into an alternative form so that we can set up a proof by algebra. So what does this blue condition mean? Equivalent to this blue equation. Do you see this? 2x minus 3y equal to 0. That becomes this. See it? Same thing goes here. Red condition becomes red equation. Again, why? This is condition for inclusion. So red becomes this red. Ready? x1, y1 gave you that. x2, y2 gave you that. And then what do you want to prove? x1 plus x2, 2x1 plus x2, and 3 y1 plus y2. This is what we have to prove. So this is a setup. And proving this, that's not too difficult because this is just proved by algebraic manipulation. This one earlier, it was a little bit difficult to see because this was proved by logical implication. But translated like this. Now this setup gave you a proof by algebraic manipulation. The proof? Simple. You want to prove this one, right? So start from left hand side and then apply some algebraic manipulation. It's easy. Break up parentheses and then move some terms around, just plain algebra, and you get 0 plus 0, and that's 0. For better understanding, I made appropriate color coding. And consequently, sum of those two vectors is in A. We just established the first condition. How do you like this proof? Didn't know what to do? Or there is a way, but it's a little bit difficult to get. Now, after this setup, it became an easy proof. The setup is the hardest part. This proof down here, that's no big deal. This setup is the big deal. Let's do this again. Second proof. Let's see. Close on the scalar multiplication. So we need arbitrary constant c. And then x comma y must be in A. Then scalar multiplication should be also in A as well. How do I translate this one in algebraic form in terms of equation? C is arbitrary, so nothing here. So this inclusion must have something to do with that. And this inclusion, again, should be coming from this. Ready? Okay, here we go. This is what you have to prove. This is a setup. Do you see? This red condition became red equation. And this black is something you have to do. And how do you prove this? That's not difficult. It's just proved by algebraic manipulation. So, you did get what you want. C times that vector is back in A, so close on the scalar multiplication as well. So, we are done with the proof, but those are very typical examples. So please remember this example very, very intimately. And of course, we're going to build upon those and then go to harder problems as well. Harder problem, what do you mean by that? I left these problems as homework problems. If you have two subspaces, U and W, then intersection is also a subspace. And then also sum, defined like this, is also a subspace. Good luck about these. These are homework problems, and they are difficult homework problems. So you'll have to spend some time on it. Okay, so much for section 1. Thank you.